Airbag activation is approximately 40 milliseconds. To fill the airbag as fast as possible, a lot of nitrogen gas needs to be produced. Therefore, at first, sodium azide has to be decomposed into sodium metal and nitrogen gas, which is the first reaction. Next, the remaining sodium metal reacts with potassium nitrate to produce more nitrogen gas, potassium oxide, and sodium oxide, which is the second reaction. Finally, the potassium oxide and sodium oxide react with silicon dioxide to produce alkaline silicate glass, which is harmless and stable compared with the other reactants, which can easily catch fire or make an explosion in a car crash. In short, airbags want to generate nitrogen gas to fill up as fast as possible and at the same time stabilize their reactants and products to produce a harmless residue.
Inside the airbag, there is a gas generator containing a mixture of sodium azide, potassium nitrate, and silicon oxide. When the car undergoes a head-on collision, a series of 3 chemical reactions inside the gas generator produce a nitrogen gas to fill the airbag and convert sodium azide, which is highly toxic to harmless glass. Sodium azide can decompose at 300 degrees to produce sodium metal and nitrogen gas. The signal from the deceleration sensor ignites the gas generator mixture by an electrical impulse, creating the high temperature condition necessary for sodium azide to decompose. The nitrogen gas that is generated that fills the airbag. The purpose of the potassium nitrate and the silicon oxide is to remove the sodium metal by converting it to harmless material. First, the sodium reacts with the potassium nitrate to produce potassium oxide, sodium oxide, and addition nitrogen gas. The nitrogen generator in this second reaction also fills the airbag, and the metal oxides react with silicon dioxide. In this, a final reaction to produce silicate glass, which is harmless and stable.
Some of the chemicals shown in the reaction, such as sodium azide, can be dangerous if exposed to skin. That's why most have been replaced by sodium hydroxide, which is safer. Trace amounts of hydroxide sodium and potassium chloride are generally present. In addition, the combustion of the airbag as a combustion engine produces carbon monoxide and nitrogen oxides. Sodium azide is considered a toxic substance since it can damage the eye, causing irritation and inflammation. Dermic contact can damage and irritate the skin exposed. Inhalation can be toxic since it can irritate the respiratory tracts, cause cough or chest pain. Ingestion can cause gastrointestinal irritation, nausea, vomiting, headache, or even death. There are certain precautions that have to be considered with the airbags. If this substance is mixed with water, it can become extremely toxic for people, biodiversity in general, and ecosystems.
Here we can see that 2 sodium azide reacts to convert to 2 sodium plus 3 diatomic nitrogen. In this reaction, the enthalpy is negative, so we can say that this is exothermic. Also, the entropy of this reaction is positive, so it's a disordered reaction. Also in here, we can calculate the Gibbs free energy and it will get a negative number, which means it is a spontaneous reaction. In the second reaction, we can see 10 sodium plus 2 potassium nitrate that react to convert it into potassium oxide plus 5 sodium oxide plus diatomic nitrogen. In this reaction, we can see that enthalpy is negative, so it is an exothermic reaction. Also, we can calculate the entropy, that it will also be a negative entropy to give that it is a less disordered reaction, that we can also say that it's like an ordered reaction. Here we can also calculate the Gibbs free energy, that it will give a negative reaction. So we can say that this is also a spontaneous reaction. In number 3, we have potassium oxide plus sodium oxide plus silicium oxide that convert into alkaline silicate glass. In this reaction, we couldn't find information about alkaline silicate glass in order to calculate the entropy in the Gibbs free energy.
Nitrogen is an inert gas that can have the properties of a noble gas if it has an ideal temperature and the pressure within the inflated airbag. Therefore, the law of the ideal gas proportionates a good approximation of the relationship between the pressure and the volume of the airbag and the amount of N2 that it contains. The ideal gas states that P times B equals nRT, where P is the pressure in the atmosphere, B is the volume in liters, N is the number of moles of gas, R is the constant of gas in liters times atmospheres divided by mole times temperature in Kelvin. R is equal to 0.08205 liters times atmospheres divided by moles times Kelvin. T is the temperature in Kelvin. There is a certain pressure needed to fill a bag in milliseconds. Once that this pressure has been determined, the gas law can be used to calculate the amount of N2 that is needed. The quantity of Na entry in the generator of gas is painstakingly determined to generate this exact amount of N2. In average, the volume of an airbag N2 is equal to 70 liters. It requires around 130 grams of iodide of sodium.
Occur inside the airbags can save lives because of the use that is given. The reaction occurs when sodium azide, a stable compound, is heated at 550 kelvins. This produces dinitrogen, the gas that inflates the bag, which is later also stabilized with other reactants. This reaction that occurs within airbags provides the passenger a 30% increased chance of surviving a direct frontal crash, because the gas that the reaction produces works as a safety cushion to the change of the momentum that the car experiences while the passenger does not. It helps to stop the passenger from colliding with the steering wheel.
But the main concern is dealing with the sodium azide propellant. When sodium azide burns, explodes, it generates harmless nitrogen gas that inflates the airbag in less than a blink of an eye. But in its solid state, it is considered a toxic material with health risks. It can affect blood pressure and might possibly cause cancer if it is somehow ingested. Also, it is important to prevent the sodium azide mixing with water, since it becomes an extremely toxic liquid that can contaminate bodies of water or even humans and biodiversity.
Airbags should be properly disposed and recycled, not only because of the material of the bag but because of the gas inside it. The sodium azide is a dangerous gas when inhaled and can burn exposed skin. If this gas is mixed with water, it becomes extremely toxic. If this enters groundwater, it becomes hazardous water. This can be very dangerous for humans and biodiversity in general. Also, it is important to find ways to recycle the materials used in the airbags in order to reduce the amount of contamination that they produce. Plastic and metal can be recovered from destroyed airbags. Therefore, they can be recycled and used in a sustainable way by creating new products from the leftovers. After materials are removed from the destroyed airbags and properly disposed of, the remaining airbag components can be recycled to form plastic pellets and metal sheets. Airbags should be properly disposed and recycled, not only because of the material of the bag, but because of the gas inside it.
Every day we use cars, but we don't really know what goes on inside them or how do they work. We need to know how they work in order to be aware of the risk of using them and to avoid damage. Learning how airbags work could open your mind on how chemistry works in real life, how we can save your life as well as damage it if it's not properly used. Chemistry is present in everything that surrounds us, and with all the knowledge we acquire while getting to know the basics, we can prevent situations by using chemical properties of matter.
The airbags that are provided in the cars are a tool that can allow us to ensure a better safety for the passengers. Therefore, it is important to understand the chemical processes, transformations of matter, and the properties that occur within the bag in order to ensure that it is properly handled to avoid any possible misuses or accidents. Moreover, having a better comprehension of the airbags and its components can help us to improve their functionality and to make them more environmentally friendly in an approximate future.
This project helped me realize that chemical equations can be found everywhere. Not only did I learn about where I can find the chemical reactions, but about its toxicity. Some reactions can be extremely toxic and dangerous to interact with. Even in things that you use in your everyday routine, like the presence of airbags in cars. People drive every day without acknowledging the toxic substances that can be released if the person gets to crash. I also learned about the impact that these substances and materials can have on us and the planet. We have to be aware of the consequences these chemical reactions can have on our surroundings and know the possible ways you can reduce the impact.
Normally, we think of chemistry as something that it is only in very specific things, as experiments or in complex things, but in reality it is in everything in our world. Everything is chemistry. What we eat, what we use, and even what we are is involved with chemistry. And as a matter of fact, the science behind the use of airbags has to do with chemistry. It is a whole reaction behind the use of airbags that involves chemicals in order to save your life in a crash. With this project, we learned that chemistry is all around us and that we need to inform more ourselves about how and why things happen.
In our daily life, we are constantly experiencing chemistry and we don't think about it too much. In this project, I learned a life-saving invention that uses the power of chemistry to fill up an airbag so fast that it protects the passenger from a collision. Having a general idea of how these transformations of matter, properties, and reactions work really make you think about how everything in our world works. Sometimes we take things for granted while there's actually a lot of thought and time put into things to create what we use on our daily basis.